Hi everyone. So we've talked about how quantum mechanics is based on the fundamental idea that fermions exchange bosons, that there are two fundamental kinds of matter, and that every force is mediated by the exchange of bosons. Now, another element that's critical to understand is this idea of indistinguishability and superposition. What I mean by that is that at a fundamental level, if I have two electrons, they are literally indistinguishable. You know, if I have two apples and they're sitting on the table, you know, they're both apples, but I can tell, you know, one's got a different shape than the other. You know, if you were to, you know, exchange them when I had my eyes closed, I'd be able to tell that you did that. Now, you say, well, that's because they're shaped different. I mean, if I had maybe two perfect spheres, like, you know, two cue balls, say, and they're the same color, you know, you spent all this time constructing them to be nearly identical and put them on the table, you might be able to fool me with my eyes, but there would always be a way for me to tell which is which, right? At a fundamental level, you know, you'd be able to, if you had enough precision, you could always figure out which is which. But an electron is different. An electron is an electron is an electron. Every electron is exactly the same. And so this exactness is critical, because if I make an observation, for example, and if I have two electrons and I see them here, and then, you know, something happens, they interact or something, and then they come out over here, I can't tell if particle A and particle B is sitting up here as particle A and particle B, or if they've switched like this in particle B and particle A. And so that indistinguishability is really critical at this level, because if it's fundamentally impossible in principle for me to distinguish the two, the theory I use shouldn't be based on that assumption of distinguishability. It should actually embrace this indistinguishability. And this quantum mechanics, quantum field theory is really the only physical theory that actually does this and embraces the indistinguishability of our fundamental particles, which is truly necessary. And so what happens is that, you know, I may have a situation where I have two particles, they exchange a boson, and they come out. So I've got an initial and a final state. That is indistinguishable because I don't measure this intermediate state. I cannot measure this intermediate state. If I do measure this intermediate state, how do I do it? What I have to do is I have to capture that photon in the middle. And if I capture it, I destroy the interaction, right? So I don't measure this. I kind of assume that it happens because I know that they interact. But I don't know if they interact through 1, 2, 3, 4, 5. You know, there's all sorts of intermediate combinations that could occur. And so quantum field theory says, that's fine. I'm going to calculate it as if I knew this were the case. I'm going to calculate the probability of this happening, calculate the probability of this happening. And what I actually measure in the laboratory is not the individual pieces here, but it's the combination of all of them. And so, in a sense, I add all these probabilities together. And not the probabilities, but the wave amplitudes. But let's just use the word probability for now. I add all these probabilities together. That's what I measure in the laboratory, and that's what I see as kind of this inverse R-squared relationship. But really, it's this flood, this exchange of particles that's happening, but that I cannot, in principle, even measure. All I can measure is the input and the output. And so this indistinguishability is what forces us to superimpose these different scenarios. And so when we talk about quantum field theory, we have to imagine that anything that could happen in the middle. And that's the fundamental rule of quantum field theory, that anything goes as long as you don't get caught. And what I mean is you don't measure the intermediate state. And so one fascinating example here is that if I have an electron just, hopping through space, blah, 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 moving in a straight line, that's actually indistinguishable from this case where the electron spits out a photon just for the fun of it and captures its own photon, basically interacting with itself. Right? These two events, because I don't measure this intermediate photon, these are indistinguishable from one another. This actually is going to take a little bit more time than this. Or this could happen. Time was the wrong word. Anyway. This is indistinguishable from that. And you can imagine all sorts of patterns in the middle, right? It's actually the total of all of these combinations that I measure in the laboratory. I don't measure this. I measure all of these combinations together. And this is what, when I do an experiment to measure the mass of an electron, for an example, the mass of the electron is dominated by this first order term, but also these second order terms impact the measurement of mass in quantum field theory. And that's an example where, in the laboratory, we measure something which we think is fundamental, but really we're not measuring the mass of the electron, we're measuring the mass of this net process. The fundamental bare electron mass is not something that we can measure physically.